Hi, and welcome to lesson 19. Today what we're going to do is exercise 8.1 from the book. And what I'm doing now is pretty much exactly what you're going to do when you do the assessment. And the idea is that we start with a linear program, and then we solve it using simplex method. You're going to note that 8.1 in the book, if you look at it, what it had originally here is these constraints were originally less than or equal to constraints. And you'll see that they also have non-negative right-hand sides. You might be wondering why that's significant, and the reason why is this structure yields an initial basic feasible solution. And when we start talking about how do we actually initialize simplex when we don't have such a nice structure, right? Like this is not true of most, you might say, or in general for linear programs. When we start talking about how do we find an initial basic feasible solution, we're actually going to use a modeling trick to basically give us this kind of structure. Because what it says is that using these variables, these new slack variables, these are going to become our initial basis. Okay, so this will be the initial basis. And you can see it's a nice initial basis because we instantly have that, S1 equal to 2, S2 equal to 3, and S3 equal to 8, and X1 equaling X2 equaling X3 equaling 0 is clearly a basic solution, and it's clearly a basic feasible solution, right? Because it's non-negative, and it's if you're going to try to solve a system of linear equations, if you have the identity matrix structure like you do there, that's always going to be a nice one to choose, right? You know that it has all the nice properties that we require of it. Okay, and it's going to be feasible as long as the right-hand sides are non-negative. Anyway, that's just to forecast what we're going to do. For now, let's just start with that as our initial basis. So our initial basis is, again, S1, S2, S3. I'll call that B0. Okay, and our X0 then is equal to 0, 0, 0, 2, 3, 8. Okay, so let's start simplex. Remember, for simplex, what we do is we have to compute, for the non-basic variables, we have to compute their directions. Okay, so let's start with dx1. Remember, in dx1, you think about the non-basic variables. These are these fellows here, and you know the components for the directions for each of those, for any direction, for any simplex direction, right? And this for x1, it's a 1 for the x1 component, 0, 0 for the other non-basic components, and then for the basic variables, s1, s2, s3, those components, we have unknowns. So it's dx1, s1, dx2, s2, and dx1, s2, and dx1, s3. Okay, so then we plug the direction into the constraints and set that each constraint equal to 0 now to solve for the direction, right? Because what we need is a dx1 equaling 0, 0, 0. That's the system we need, which is equivalent to saying, in this case, I'll plug in 1 for x1, 0 for x2, 0 for x3, and then dx1 s1, dx1 s2, dx1 s3 for s1, s2, s3. And I get the 1 plus dx1 s1 equaling 0. I have 2 plus dx1 s2 equaling 0. And finally, I have 6 plus dx1 s3 equaling 0. And note that that's just the x1 column because I've substituted in 1 for x1 there. And then it's the S1, S2, S3 from dx1, S1, dx1, S2, dx1, S3 being substituted in for S1, S2, S3 respectively. And of course, it's equal to the 0, 0, 0 vector because regardless of the right-hand sides in the original equality constraints, what I want is that this direction won't affect those equality constraints. So I need a dx1 to be equal to 0, 0, 0. I don't need anything special to solve this equation, right? I know that this is just d s1 x1 equals -1, dx1 s2 equals -2, and dx1 s3 equals -6. Okay, so now I have to do the same thing for my dx2, except it's 0, 1, 0, dx2 s1, dx2 s2, and dx2 s3, okay? Note that the 1 has now shifted over to the x2 component, right? Because that's this direction. And when I do the same calculation here, dx2 now has to equal, let's put our vector signs here, has to equal the 0, 0, 0 vector. I see that now it just shifts the column, right? It's now the x2 column that gets pulled out, and it'll be 1 plus d s1 x2, 3, I had to check it because to make sure, ds2 x2, this equals 0, this equals 0. And it's got the same coefficient in the third equation. It's 6 plus dx s3. The fact that it's the same, of course, is just coincidental. And here I can solve this. And we have dx2 s1 equaling -1 again. dx, so that fourth component is the same, but the fifth component is different. dx2 s2 equals -3. And dx2 s3 equals -6. So the overall direction then is given there. And I just realized I didn't write the overall direction up here, so let me just do that quickly. I'll put it in green just to set it off. dx1 here is equal to 1, 0, 0, -1, -2, -6, and here dx2 is equal to 0, 1, 0, -1, -3, -6. Okay, so dx3, I hope you're starting to understand how we really like it when computers get to solve this for us. It's 0, 0, 1, dx3 s1, dx3 s2, and dx3 s3. Again, I want a dx3 to be equal to the 0, 0, 0 vector. And I see it's going to pull out the third column. So that's 2, 4, 2. So it's 2 plus dx3 s1 equals 0. 4 plus ds2 x3 equals 0. And 2 plus dx3 s2 equals 0. That's just from this matrix multiplication. And that means that ds1 x3 equals -2, dx3 s2 equals -4, and ds3 x3 equals -2. Okay, so that means that our direction now, dx3 equals 0, 0, 1, -2, -4, -2. Okay, so we have all the directions solved, and what I need to know now is, well, what is the reduced costs? Which of these directions should I pick, right? We've calculated all the three directions. We had 3 non-basic variables, and now we can calculate what is going to be our reduced costs. Are these things improving or not? And it turns out they all are. Now, how do I know that? Well, it's because the c vector here, remember what those are, is the coefficients of in the objective. So it's these coefficients here. Now you might say, how, so those coefficients look like 8, 9, 5. And of course, there are 6 variables, remember, because of the slack variable. So it's actually the other variables have a coefficients of 0, 0, and 0. Okay. So so remember that this is equal to the gradient. The gradient of my objective function is the same thing as the c vector, because we have a linear function. So the reduced cost of x1, which is the gradient transpose dx1, I can see that's just equal to 8, because it's zeros. It's got a 1, it's 1, 0, 0, negative 1, negative 2, negative 6, but those negative numbers all get the 0 coefficients. So that's just 8. Similarly, c bar x2 equals 9, and c bar x3 equals 5, which means that the improving direction that I'm going to make because of the Dansish pivot rule is x2. And so that's the step size I have to go with, and that's what I have to do next. Okay, so this is going to be the direction I choose, which of course is this direction down here. So 0, 1, negative 1, negative 3, negative 6. And now I have to do step size. Okay. Okay, so now I have, just to refresh our memory of where we're at here, we're going to have x0, which is equal to 0, 0, 0, 2, 3, 8. We're using dx2, which is equal to 0, 1, 0, negative 1, negative 3, negative 6. Okay, and we want to know, well, I need that x0 plus lambda dx2 to be non-negative. So I need this to be greater or equal to 0, 0, 0, 0, 0, 0. Now note that on the non-basic variables, this is never going to be an issue, right? Because this is going to basically say 0 plus lambda times 0 is non-negative. That's always true. And I'm writing this down. I think this confuses students that I write these inequalities down when they don't really matter. But I do want to keep consistent with what we're actually doing. It won't be wrong if you don't write down the non-basic variable inequalities for this check. This corresponds in the min ratio test. It always ignores the directional components that are not non-negative, right? And that's always true for the non-basic components of the direction, because they're either 0, all of them are 0 except for one component, which is a 1. So that's always non-negative. Anyway, I just wrote that down so you can see it. The ones that are important are going to be this 2 plus lambda times negative 1 has to be greater or equal to 0. You can see that can be violated if I make lambda big enough. And the same is true for 3 plus lambda times negative 3. That has to be greater or equal to 0. And 8 plus lambda times negative 6, greater or equal to 0. And we can see these ones lead to lambda has to be less than or equal to 2, or that gets violated. Lambda has to be less than or equal to 1, or that gets violated. And lambda has to be less than or equal to 4/3, or that gets violated. And so we see that the most restrictive of these equations is 1, and I get that my new solution, the new basic feasible solution, is x1, which is equal to, and I just plug in this lambda equals 1 into this equation here to get this. And I see if I make that 1, then well, what I get? I get 0, 1, 0. Then I get 1, because it's 1 times -1 added to 2 is 1. -1 times 1, -3 times 1 plus 3 is 0. And -6 times 1 plus 8 is 2. And that's my new basic feasible solution. And the new basis, so the leaving variable, was this S2, right? And you see that the leaving variable comes from whatever inequality wins the min ratio test. And then the entering variable was x2. So my new basis 1, is equal to x2, s1, s3, right? x2 entered the basis, s2 left the basis. All right, so that was one complete pivot, and we keep moving. We have to now do new directions, and we have to see whether there's any improving ones. If there are, then we'll keep on executing simplex. If not, then we stop because we're done. And in this next pivot, what we're going to see is I'm actually going to stop this video and do another video where I can do some of the directional computations on the computer, because the computations get harder. You're going to notice that the direction computations that we did before, these fellows here, they're actually easy. We can do them by hand, so to speak. I just don't want to do that. Yeah. These are easy enough to do by hand. For a hand calculation. When they get harder, as we're going to see, I'm going to suggest that you go to the computer, because it'll be a little easier to do. And I'm going to show you how to do that. All right, so let's think about our basic variables. We have dx1, our basic variables are x2, x1, s3, so we need a direction for each non-basic variable. So in particular, we need a dx1. Okay, so now we had a sort of simple looking structure before. We have to be a little careful that we keep in mind what our basic and non-basic variables are, because now it's not like all the basic variables are in a row and all the non-basic variables in a row. Now they're kind of jumbled throughout the vector. So here we have a 1 component for our x1 component. That's still the same. But now x2 is basic, so it's unknown. So it's dx1, x2 now. This is x3 is non-basic. That gets a 0 because we're not changing that. We have unknown s1, so dx1, s1. The 0 in the s2, and the dx1, s3. Okay. So pay special attention to how, because the pattern of the basic variables has changed in the vector, the pattern of how we set up our components in the direction have also changed. We still need to satisfy this matrix vector equality, where this matrix vector product equals 0, 0, 0. But now it looks a little different, right? Before we sort of had this thing that we could easily compute by hand. Now we have equations that are a little harder to satisfy, because the pattern of the basic variables have changed. Because now we have two sort of not very easy columns to look at. So we have a 1, so we have 1 plus this unknown d, x2, x1, plus d, x1, s1 equals 0. Okay. If you plug this vector into the constraints, you're going to see that's what pops out for the first line. You have 2 plus d x1 plus 3. To be a little careful here. Plus 3 dx1 x2 equals 0. And then you have 6 plus 6 dx2 x1 plus dx1 s3 equals 0. Now I do not want to solve that, and I'm not going to try to solve that by hand. I could do a backward substitution and blah, blah, blah. It gets tedious, so I'm not going to do that. Instead, what I'm going to note is that this is equivalent to saying that if you think about it, this column is constant, and these are all coming from the matrix formed by the basic columns themselves, okay? And they're just multiplied by the basic variables. So I'm going to spell this out. I'm going to say, look, I'm going to bring the 1, 2, 6 to the other side. So, and then I'm going to express this as a matrix and a vector product. And what I see is that it's 1, 1, 0, 3, 0, 0, 6, 0, 1 times the unknowns here, dx1, x2, dx1, x3, I'm sorry, x3, what did I say? Dx1, s1, and dx1, s3, and that equals the vector -1, -2, -6. Well, what is this? This is, let's call this matrix B1. This is a script B1. This is a regular B1. And it's times my basic components. So I'm going to call this the vector dB of x1. And it equals minus, and I'm going to call this AX1. This is the x1 column, okay? And we're going to see, you can see that this is, because this is a basic solution, I know that the determinant of B1 is not equal to 0, and I can see that dB1 x1 equals B1 inverse minus B1 inverse AX1. Okay, and that's the calculation I'm going to do on the computer. All right, now I haven't done that calculation yet. I'm going to do it after I finish showing you that the same pattern holds true for dx3 and ds2. Okay, so let's do that. All right, so remember what we have. We have dx3 equals, our pattern is, the x1 is a non-basic variable, but I'm checking the x3, so it's 0. x2 is basic, so this is dx3, x2, that's unknown. 1, because this is the x3 component. dx3, s1, that's unknown. 0, because s2 is non-basic, and I'm not checking whether or not I should add that. And then ds3, x3. Okay, again, I need that a dx3 equals 0, 0, 0. This is equivalent to putting this vector into this vector dx3 into the constraints. I see that leads us to a dx2 x3 plus 2 plus ds3 x3 equaling 0. I have 3 dx2 x3 plus 4 plus 0 equals 0, right? Because there's a 0 coefficient for the S3 variable in the A matrix there. And then finally, I have 6 dx2 x3 plus 2 plus d s3 x3. And I just noticed a little typo here. This should be dx1, sorry, dx3 s1. Sorry about that. So make sure that you see why that's true. And this last one, equality is also 0. And again, I see the same pattern, just with a different column. I see that if I bring this 2, 4, 2 to the other side, and then what I'm going to have is this matrix 1, 1, 0, 3, 0, 0, 6, 0, 1 times, again, now it's x3 is the non-basic variable, but it's still it's dx2, it's dx3 s1, and dx3 s3, and it equals -2, -4, -2. Okay, and if you look at that matrix, right, it's the same matrix as we had over here. It's the same, it's still B1. It's still this B1 matrix. It's B1 times, now it's the dx3b basic components, but it's still the same basic components. And now instead of -a1, it's instead of -ax1, it's -ax3, right? Which is the same thing as that, and it's also the same thing as saying that db x3 equals b1 inverse with a minus sign. I keep on forgetting to say minus. Let's make that really clear. It equals minus b1 inverse a x3. Okay. All right, and we can now do the same calculation for the ds2, right? Again, the basic variable pattern has changed. So the non-basic variables are in different places as in the first iteration. So this is 0, ds2 x2, unknown, 0, because x3 is non-basic, but we're not adding that, we're adding s2. ds2 s1, 1, ds2 s3. Okay, I need a ds2 equals the 0, 0, 0 vector. It leads to, again, this substituting in the ds2 vector into the constraints, setting them equal to 0. That's going to be dx2 s2 plus ds1 s2 equals 0. Note that in this set of equalities, the column is much simpler, right? Because the column is an s2. Slack columns are always sort of these simple identity columns. That's their property. Okay. Here we have 3 dx2 s2 plus 1 equals 0. And then you have 6 dx2 s2 plus ds3 s2 equals 0. This one I would say you could probably solve in your head, but I want to show you the pattern. So again, it has the same matrix 1, 3, 6, 1, 0, 0, 0, 0, 1 times your dx2 s2 now, ds1 s2 ds2 s3 equaling 0, -1, 0. And that's from bringing this -1 to the other side. There were no other constants on the left-hand side because of the property of the slack column. And again, this is just equal to b ds2 basic 1 equaling minus AS1. Okay. So this is equivalent to saying, again, that D B1 S2 equals minus B1 inverse AS1. Okay, I'm going to stop here for this written portion and go